Okay, in this next section, we're going to cover two sections, 21.5 and 21.6, power in an AC circuit and resonance in an AC circuit. Um, so let's bring up the PowerPoint and go to the next slide. And we're here. In an idealized situation, there are no power losses associated with pure capacitors and pure inductors in an AC circuit. A pure capacitor, by definition, has no resistance or inductance, and a pure inductor has no resistance or capacitance. Of course, these definitions are idealizations. In a real capacitor, for example, inductive effects could become important at high frequencies. Let's take a look at the power dissipated in an AC circuit that contains only a generator and a capacitor. When the current increases in one direction in an AC circuit, charge accumulates on the capacitor and a voltage drop appears across it. When the voltage reaches its maximum value, the energy stored in the capacitor is given in the equation shown. Potential energy of the capacitor is equal to 1/2 C times the delta V max squared. This energy storage is only momentary. When the current reverses direction, the charge leaves the capacitor plates and returns to the voltage source. During 1/2 of each cycle, the capacitor is being charged, and during the other half of the charge, the charge is returned to the voltage source. So the average power supplied by the source is zero. In other words, no power losses occur in a capacitor in an AC circuit. In a similar way, the source must do work against the back EMF of an inductor that is carrying a current. When the current reaches its maximum value, the energy stored in the inductor is a maximum and is given by the equation PEL equals 1/2 Li squared. When the current begins to decrease in the circuit, this storage energy is returned to the source as the inductor attempts to maintain the current in the circuit. The average power delivered to a resistor in an RLC circuit is shown here. P average is equal to IRMS squared times the resistor. The average power delivered by the generator is converted to internal energy in the resistor. No power loss occurs in an ideal capacitor or inductor. Okay. Let's substitute R from Ohm's law into our power equation. Now we have an alternate equation for the average power loss in an AC circuit. So P average equals IRMS squared R. If we solve for R, we get V. Knowing that R is VRMS divided by R, it now becomes P average equals IRMS times VRRMS, okay? Which looks like the original term for power. Power equals I times V. We can use the voltage triangles shown here, where we see that the voltage drop across a resistor can be written in terms of the voltage of the source. Delta V R MS equals delta V times cosine phi. That means the average power delivered by a generator in an AC circuit is this relationship, where the quantity cosine phi is called the power factor. So V average is equal to IRMS times delta V RMS times cosine phi. This equation shows that the power delivered by an AC source to any circuit depends on the phase difference between the source voltage and the resulting current. This fact has several interesting applications. For example, factories often use devices such as large motors and machines, generators, and transformers that have a large inductive load due to all the windings. To deliver greater power to such devices without using excessively high voltages, factory technicians introduce capacitance in the circuits to shift the phase. This ends the power in an AC circuit section. The next section we will discuss is section 21.6, resonance in the series RLC circuit. And I think I'm doing them both together, so we'll just continue. In general, the RMS current in a series RLC circuit can be written as shown. I RMS equals V RMS over the impedance. And that equal to V RMS divided by the square root of R squared plus X sub L minus X sub C quantity squared. From this equation, we see that if the frequency is varied, the current has its maximum value when the impedance has its minimum value, which occurs when X sub L equals X sub C. If X sub L equals X sub C, then that quantity squared term becomes 0. In this situation, the impedance of the circuit reduces to Z equals R. The frequency at which this happens is called the resonance frequency of the circuit. To find the resonant frequency, set X sub L equal X sub R. And you'll find that the so 2 pi f L, f of 0 means the resonant frequency. 2 pi f L equals 1 over 2 pi fc. And if you solve for f, you get 1 over the square root, 1 over 2 pi the square root of LC. That's how to find the resonant frequency. Remember that. Okay. In this figure is a plot of current as a function of frequency for a circuit which has a fixed value of both the capacitance and the inductance. From our RMS current equation, we have to conclude that the current would become infinite at resonance when R equals 0. Real circuits, of course, always have some resistance, which limits the value of the current. The tuning circuit of a radio is an important application of a series resonance circuit. The radio is tuned to a particular station which transmits a specific radio frequency signal by varying a capacitor which changes the resonance frequency of the tuning circuit. When this resonance frequency matches that of the incoming radio wave, the current in the tuning circuit increases. So this ends the resonance in a series RLC circuit section. The next section we will discuss is section 21.7, the transformer.